So, do y'all have any questions on subroutines? Yes, no?
Nope.
Everybody okay? Everybody okay on how to create them? Jump subroutine, everybody okay with that? So how do we create a additional program file for a subroutine?
Can it go under program and add?
Yeah, we come over here under program and right click, right? Right, and then choose what? New. Yeah, let me go offline. So right now we have, this file don't have any subroutines. Let me open one that does have a subroutine. I didn't see one in there. Wow.
The jumping shots, J and D and E2, right?
But there's a difference between a jump instruction and a jump subroutine. So what's the difference between a jump instruction and a jump subroutine?
Yeah, I guess that needs to be my question then. I didn't write that down.
A jump instruction only takes you within the program file that you're in.
Right.
You can't leave.
Oh, yeah.
We can jump forward or we can jump backward. It's actually what we call an instruction pair. So you can't have a jump without a label, right? You understand that? So you're going to jump to a label. You can jump forward or you can jump the program back, but it's going to be within a program file.
And was there like, do we have to type anything in different to jump? Or what do we have to type in different to jump from the one subroutine to another? Or is it still the same command jump?
No, it's a jump subroutine. So we have a JSR, we have a JMP, which is a jump, and then we have a JSR, which is a jump to subroutine. These are all inside your program control. I think it's what it is. So program control. So here's program control means these are the instructions where you can actually change the sequence of the way the program actually runs. So normally the scan starts in line 0 or rung 0 because 0 is the first rung and it goes from top to bottom, right?
Sure.
But using the jumpers and it goes rung 0, rung 1, rung 2, rung 3, rung 4. With the program control instructions, we can change this sequence. So we jump forward.
I remember that. The jumping forward and the jumping back creates a loop.
Now we could jump back would create a loop. Jump forward would make you skip over. So like we said, you might have a counter that where you load either 6 things in a box or 12 things in a box, and you can just flip a switch. And you could use the jump instruction to jump over one, right? Jump over the one that runs 6 and load it with 12. That makes sense?
Sure. Just making sure I remember the commands when I have to do it. Because that's my biggest thing is remembering those. Like the move instruction, like I was confused till I remembered how you said to do it. And then once it's done, it's simple.
Yeah, move instructions and
most of my like memory, I have to think do it once after he says it.
So what we would do, we would have a bunch of rungs. I've got a bunch of arrows. We're same chapter with jump subroutines, but we had an answer about a jump instruction. So the jump instruction, they're inside the program control, or we can go up to this main menu, and we know they're jumps, right? And all these are in alphabetical order. So here's a jump, and it's an output instruction. How do I know it's an output instruction? Because it automatically jumped on the right? Understand? Now jump to subroutines, we start off with Q, and then we come up and we put a number, like Q1. And you can give it a label, guys, but we're gonna move on. Now you cannot have a jump unless you have a label. So the label here's label. So somewhere down in label is a what? It's an input instruction. So what I would do is I would come up here and give this the same name, Q2, colon 1. Sorry. Q2? Q2, right?
Q2.
Yeah. Q2 colon 1. And then what that tells it is, if I gave this a symbol, by the way, I could do the same thing over here. What it says, okay, I'm going to jump, when it hits this instruction, it's going to jump over what? Rung 2. It's going to jump over rung 1. But I could come down here and put another jump instruction.
You could do that for like multiple rungs. Like, so you only have to do it where the label is. The label is the start of the jump.
No, the jump is the start of the jump. The label is where it goes to. The actual term is jump to label. So it's a pair. You can't use a jump without a what? Without a label, right? That would be like me saying everybody go to, and then I stop. And what was the first thing you'd say? Where? And that's what the label says. The label is telling us what? Where, right? The jump can be conditional, so I can come up here, I can put compare instructions, so the jump itself can be conditional.
And so labels can also be used for JSRs too, right?
No, that's a subroutine. It's called jump to label. There's no such thing as jump to subroutine. Okay, a subroutine is going to take you to a completely different data file. Program file. It's not going to have anything to do with this. So jump and labels are within a program file. Well, somewhere there's a jump or a go. Or a go-to, yeah. So we do a lot of jumping around inside, especially on robots. If we want it to loop, then we have to put a jump at the bottom. It would be a jump here. Robots, programming languages use two terms for this. They're not all the same. Some programming languages call it go-to label. So and go-to is one word, but it still works the same thing. So some programming languages use the go, and this is on the robots over there. Some of them say go to label, some of them says jump to label, and it's the exact same command. PLC calls it jump to label. So if I was going to use a JSR, then I would come up here. First of all, a JSR, we got to create a new program file, and we should give it a name. So what happens is now over here I have what? I have two program files. We have the main program. So this, I'm going to rename this, I'm going to call this main. So this is the main program. So every program has what we call a main loop or a main program. Now what I could do, and this could be in here. So I'm going to go back to my So here I'm going to use a JSR, and they are not the same. And we do have a branch subroutine, but I don't think they're going to talk to that in here, which is weird. So here's the JSR. Okay, didn't come in there. So the JSR is considered an output instruction, just like the jump. It's coming in box format. This is in the JSR. I mean, the jump instruction is in coil format. The jump instruction is in block format. Here, to tell it what subroutine, we start off with U, then we put a colon, and then we put the number of the subroutine we want to go to, 3. And then we can give the subroutine a name. Okay. So now what I would do, I'm going to come over here and double click on this one. And now this is the subroutine. So over here, we would come over here. Now we're supposed to put an SBR instruction up here. It's optional, but what it does is it identifies. So we have 2 types of routines that we can run, additional program files. We can run what they call an interrupt service routine, and we can run what we call a jump subroutine. Well, what we like to do, since we got 2 types of files that are considered routines, we need to be able to easily identify which one is which. So what we have is we have another instruction that we use inside the program control called an SBR. And what this does, this identifies this file as a subroutine. Now, the only little problem that we have with the RS Logic is the SBR is an input, and it's always examined true. So this will never, ever be conditional. So I've got an input. What do I need? If I've got an input, what do I have to have? Yeah, I've got to have output. So what we'd probably use here is we don't want to sacrifice an output that's true all the time, right? You understand that? So what we would do is we would come up here and we'd use one of our bit files.
So you could set up something like, say you have 3 rows, 3 different subroutines. You could have them all set up with different lights. Each light will come on when that subroutine is running.
When the subroutine is running, right?
All right.
Now here, so what we're going to have to do for 500 is we're going to have to identify B3. We're going to use one of our B3 files, one of our B3 bits. Now what we do at the end of the subroutine, so we'll have everything we want to do when the subroutine runs would be between rung 0 and then the end rung, right? You understand that? What we would do on the rung before this, what we would do is we'd put a return instruction. And what the return instruction does, it causes the program to go back to the rung after the JSR. So it automatically goes back to the previous program or whatever program file that called it, right? You understand? And it'll go back to the next rung. So what do we use to so it? They're not the same. Jumps are within a program file. JSR takes us to another program file. And how do we know when and now the return can be conditional. If you have a conditional return, then what would happen once it gets into your subroutine, it's just going to live inside the subroutine. So we like that because now we can run the subroutine over and over and over and over again and get all the bugs out of the subroutine. So we can make that conditional. We don't have to. Now the problem we have is that your input, if it's not running the subroutine, the inputs are not being scanned and the outputs are not being updated. So what that means is if you come out of a subroutine with an output turned on, it's going to be turned on until you get into that subroutine and tell it to do what? Turn it off. And we can have a lot of subroutines. We can go all the way up to 999. Of course, what determines how many devices are inside a program? It's going to be dependent on how much memory you have in your PLC, right? So that's one of the things when you buy a PLC is you specify how much memory you need inside it to do what you need to do. Are we okay? So what's the difference between a jump and a jump subroutine?
One's inside program, one's to a program, or
The jump it's actually a jump to label, right? You understand? We call it a jump, but if you look at it, it's a jump to label, which means it requires a what?
LBL.
It requires an LBL, yellow label. And we could have a ton of them. We could jump backwards, we could jump forward, we could jump within a jump. Just like I could come over here to this subroutine and do what? Oops. So I could come within this subroutine, and we'll make this one some conditional, and I could put another what in here. I could come over here and of course I'd have to create another program file. So we'll probably get an error on this one. So and then of course what I would have to do over this one, I would write my subroutine over here, and then we need to start it with a what? An SBR, right? Which is optional. It's optional, guys, but we need to do that because, like I said, we have two types of programs that appear to be subroutine. One of them handles interrupts, one of them handles subroutine, and we'd need to be able to easily define the subroutine. So we would start this subroutine with an SBR, which identifies it as what? Subroutine. It's an input instruction that's going to be examined true every time the subroutine runs. So what we need to do is we need to use one of our B3 files over here. And we can give it a name too. And then we would come over here at the end of this subroutine, and our last instruction, not a reference, Rich. These things are so small. And then we could end this with a return from subroutine. Oops. So how would this one work? Well, we call these nested subroutines. And it keeps up with the processor automatically keeps up with where it needs to go back to. So when it hit this return right here, it would go back to this subroutine and it would run whatever rung was right in here. It would go back to the next rung in the subroutine. So when you call a subroutine, how does it know how to come back? Well, there's a thing that the book talks about called a stack.
So if we just put the return in like that, it'll automatically go back to the line above.
No, it'll go back to the subroutine that called it. This is not the subroutine. This is subroutine number 3. It was called from the main. So subroutine 3 was called from the main program. Okay. So when it hits that return over there in subroutine 3, it's going to come back to program file 2. it comes back to whoever called it. So over here, this is subroutine, this is Rich, it's called in subroutine 4. So when it comes over here and sees this rung right here, it's going to go back to program file 3, right? You understand that? So we call these nested subroutines, and we can, and if the PowerPoints are still up here, so look how many nets they have here. So this guy says JSR, it goes to file 6 is what they're using. Here they have a jump subroutine to file 7. Here they have a jump subroutine to file 8. This return is going to take it back to 7. This return is going to take it back to 6. This return is going to take it back to the main program. So it always goes back to the routine or the program file that calls the subroutine. And we call these nested, this is called nested subroutine. So a nested subroutine is when a subroutine calls a subroutine. And we say call. That's what the term we use. So we call subroutines. And by the way, this is not in your book, this is right out of your book that covers nested subroutines that well. This is right out of the RS Logic manual for the field.
This on that book?
Well, how many levels can we go? Well, we can go all kinds of levels, and it always knows its way back home, where it came from. Right? Does that make sense? So for every JSR, and this one can call that one. I mean, so yeah, this is not a really good example. So I could come over here and let me run my PowerPoint so I can draw on it. So down here, right here, I could put a JSR. I could put a JSR 6, right? And then it would do what? It would actually go back in here and run this subroutine, and then when it hits the return, it would go what? It would go back here. So I mean, subroutines, and we do this all the time in computers, because you got how many applications you think uses the keyboard on my computer right here? How many programs do you think runs the keyboard? One. Well, how does all these different programs have the ability to grab stuff from the keyboard? We use what? Subroutines. We use subroutines. And subroutines can cause anything anywhere, right? You understand, like using the USB port. How many programs in the operating system run the USB port? One. Well, what we do is we can do what? We can call that as many times as necessary, and it always finds its way back home, right? To the actual program that calls it. So this is really means a lot. So instead of me writing a code for running the keyboard in every application, and that's what we call them. We call them applications, right? We call it because they apply the operating system. So when I load in Microsoft Office, it doesn't have a program that runs the printer. That's built into the operating system as a what? As a subroutine. And we call it an API, an application program interface, that they provide to these people that write these applications, so they know where these subroutines are at. So yeah, if it wasn't for subroutines, computer programs would be what?
Really long.
Yeah, because everybody that needed to use a display would have to have a program that runs a what? Display. We call them drivers. So these are basically little subroutines that are built in, that we load into the operating system, right? You understand? So these other applications, and that's why they're called applications. They apply the operating system, right? So an operating system is just thousands of subroutines, and we call them drivers. And a lot of times when you install a new piece of hardware, it'll come in and say you have to do what? You have to install the driver again. So yeah, when we put together a computer, one of the first things it comes with is a disk, and we have to load the drivers for you know, your network card, you have to let, so if I was to install a new operating system on this thing, the network wouldn't even, the network wouldn't even work anymore. I'd have to, before I did what? Yeah, because Microsoft does not know who makes the network card that goes into your computer. So what they do is they have a drivers. So when you buy we used to build all our computers here. You can probably, on some of you can tell. So back in the back of the PLC lab, all those computers back there, we were built. The students built them.
You know the new motherboards are?
Huh?
You know the new?
Yeah,
Where they have built-in graphics cards and a lot of them now?
yeah, a lot of it do that, but some of them still allow you to, we still have some, they call it a PCI IPE interface, PCI Express. Most of them comes with a high quality video card, so you can still choose the video that you want.
Yeah, but like, the way I was told when I was buying mine is that it's just pretty much for maintenance if your main video card goes out.
No, you still get, most high-end motherboards allows you to choose the video that you want.
Yeah, but like,
These guys right here, you get, these guys right here, you get what you pay, you get what you pay. So everybody okay on subroutine? And jump, y'all know the difference, right? So jumps are, it's a jump to what? We call it a jump, but technically it's called a what? Jump to label. You have to use those as pairs. The problem is though, is that the PLC does the scan all the time. And another good example is the keyboard on the computer. How often does the subroutine for the keyboard run on the computer? It's not technically a subroutine, by the way. It's this thing we're fixing to talk about.
Wouldn't it be constant?
Well, why?
Because it has to check if anything's been pressed, or
Why? Why can't the keyboard say, "Hey, I've got something for you," and then that way you never even have to go to the keyboard until I come up here and touch. So right now, this computer is not scanning this keyboard at all. It's not scanning at all.
oh,
Okay. The analogy we like to use is in a class. So when we talk about the way you're talking about, what we would have to do is it would kind of be like the PLC does. So it's coming down here. It says, okay, hey, do I have an input? Okay, if I don't have an input, then I don't need to, I don't need to run the logic, right? Okay, then I come down to the next one, the next one, the next one. Well, the problem is that if you got something that's got an extremely high priority, or if you want to, something that you're going to use all the time, instead of you coming up here and scanning it all the time, why don't you let the device say, hey, why don't you come out here and scan it? And then that way, I'm not wasting all my time reading the keyboard when how often am I touching the keyboard right now?
right now, none.
So this would be like me coming in and giving a lecture, and every once in a while I stop and I come up here and I say, Sierra, do you have any questions? I say, Jaden, you have any questions? And whether you have a question or not, I stop my scan and I go to everybody in the class and say, do you have any questions? Even if you don't have one. Now, what's a more efficient way to run a classroom? The more efficient way for me to be is just to get up here and lecture, and if you had a question, you would interrupt me, right? You understand? Interrupt me.
So it's like an interrupt in the computer.
That's right. So what we do is when I come over and press a keyboard, it generates an interrupt. Then the computer stops what it's doing, goes out there and scans the keyboard, gets the information to the keyboard, brings it back in, then it's off and running. It don't need to go out there and scan the keyboard all the time. Unless what? Unless there's an input or an interrupt. So we can see this. It's hard to find on Windows 10, even though it's still there.
The mouse the same way?
Huh?
Like the mouse?
Mouse the same way, generates interrupts. So right now, is it reading this mouse? No. But as soon as I move it, the circuitry that runs the mouse generates an interrupt, and then it goes and reads it. If I was to have to go out here and scan everything in this computer, every program had to scan everything in this computer, you talking about slow, everything would be what? Really slow. So we deal with interrupts, and this guy's got all types of interrupts, guys. We can come up here and let's see where we can find that at. Program files, accessories, system tools. And then we're going to look at system information.
So has it always been this way, or?
Ever since, well, no, it's just that they learn.
Yeah.
They learn. So you start off with these little 4-bit microprocessors running a cash register. And then you get moving up, and you say there's got to be a better way. There's got to be a better way to do it where we're not constantly scanning keyboards when keyboards are not that very seldom used.
Computer that was built in the 90s to a computer that's built now.
Yeah, we'll show you all the interrupts in here. It's unbelievable how many interrupts they use now. And we actually set up our priority too. So some interrupts are going to be really high up here. They need to be taken care of. Some of them can be ignored for a little while, right?
Yeah. This has more processing power than a computer built in the 90s.
So hardware interrupts, there it is right there. So these are all the devices in this computer that has the ability to generate an interrupt. Usually up at the top is the highest priority, and the bigger the numbers you go down. We're not even halfway down this, guys.
Where'd you go to find that?
We went to system information. So we go over here and go to system, all program files. Then we go to system information. I'm sorry, accessories, duh. Accessories. And inside accessories, we'll find system information. Y'all help me. Oh, I'm sorry. We need to go to system tools. There we go. Then we go to system information. And this tells you your hardware recess. This tells you all the addresses in the computer. So here's all the addresses all the different I/O devices have inside this computer. So there's the speaker. That's the internal speaker right there. So everything's got an address, right? You understand that? Here's my interrupts right here. And so right now in this computer, we've got up to, I don't know what those bottom ones are, 190 different interrupts on different devices that have the ability to generate interrupts.
So does it?
And right here, what's interrupt 1?
System timer?
Keyboard. So this is the ThinkPad, little slide pad that I have.
So the whole keyboard is just on that one?
An interrupt because all of it's
I
considered.
didn't know if it had it broke down into each key or.
No, it one interrupt because all we're saying is that the driver will figure out the key.
Okay.
All we're saying is a key on the keyboard has been pressed. You need to run the keyboard scanning program to see which key is. Then it goes out there and runs the interrupt service routine, which we call the driver. But some of them are subroutines, some of them are actually interrupt service routines, but they're very similar. It causes another program file to run, right? You understand? So if we're going to use interrupts, we're going to set up another program file just like we do with subroutines. And so that's why you need to identify whether it's a subroutine program file or whether it's an interrupt stuff. So this is all interrupts. Some of you probably know numeric. So the CMOS so there's the real-time clock. So that's the real-time clock, wanting to be updated all the time. We have a ThinkPad upward pointing device. That would be the little thing in the center. High definition audio. Here's the audio controller that generates an interrupt. Some of these have been around, the same interrupts for years. You can go back to, there's some that's not up here anymore, but you can go back to the original IBM PC, and that keyboard interrupt was IRQ1 then. So this has been IRQ1 for generations, right? And then also the sound card too. Audio, no, it hasn't been this is high definition. The regular internal generator. So these are interrupts. So what happens is these guys have the ability to get the process of the attention no matter what's going on. Unless we can ignore it. So these are what we call interrupts. So what we can do if I get into a high priority situation where I don't want the keyboard to interrupt, it would be so it's just like this. You come up here and I'm up here lecturing and you raise your hand. What do I usually do? I usually don't stop instantly and save the letter that I'm on. I usually complete my thought. Well, what I've done is I've masked you off for a certain amount of time while I get the information out of the way, right? You understand? So these are all what we call maskable interrupts, which means we can enable and we can disable these things. So if I've got a real high priority program, that program has the ability to disable the keyboard interrupt. If they disable the keyboard interrupt, you can be on the keyboard from now into doomsday, and it's not going to honor that keyboard till it gets through with what it's doing, right? You understand? And so, yeah. So these are all maskable. So what we'll look at is what we call, we do have some extremely high priority interrupts, which usually are not available to the user at all. These are taken care of inside the PLC. These are called non-maskable interrupts. These would be like your faults. You have a major fault. I don't care what you're doing, it's going to stop everything. It's going to run a fault. It's going to turn that red light on up there, right? And nothing, it's not scanning, it's not doing anything.
Kind of like when your computer gets too hot and it wants to shut everything down.
It might, I don't know if it generates, usually the non-maskable interrupt, we use them for power situations and stuff like that. And usually it only had one non-maskable interrupt.
Blue screen of death.
The blue screen of death, yeah. That's not a non-maskable interrupt, that's just a program crash. So we need to say, okay, I want to be able to detect this input no matter where it's at in the program. If you're going to do that, then you need to put that, you need to assign that to what? To an interrupt, right? You understand that? So interrupts are usually hardware generated. We do have some software for traps and stuff like that. They got one where you can actually trap a fault. And if you trap the fault, then the processor's not going to lock up on you. It'll give you, sometimes it gives you the ability to get out of the fault. A method available to hardware devices that can force the PLC to run a specific program file. Allen Bradley supports 4 times. User event interrupt. We're not talking about that one. High-speed counter interrupt, which is really, really cool. What we had, even though I said I wasn't going to talk about it, you need to understand, we're dealing with one of the main sensors that we use now is what we call an encoder. And so what these encoders do on the devices they're trying to check the speed, it sends out a series of pulses. And we come in and we count those over a certain amount of time. So we could set up a counter and we could count it over like a second, and then we could stop it and multiply it by 60, and then that would give us the what? The actual revolutions per minute. After we figure out what the counter does, one of the little encoders that we have, this little guy right here gives us 2100 counts per revolution. The encoder's on the this is another. So this is really interesting. So while the robots use, this is what a lot of robots use. These are what we call quadrature covers. So if you look at it real close, you notice it's got 2 LED sensors that's on it, and then it's got gaps cut into the encoder wheel. So it's got 2 sensors, and if you look at the encoders, the little slots are all set by 90 degrees. So if this one was right there, then this one right here would be right here. And so what happens if the encoder turns in one direction, if we call them channel A and channel B, if it turns in one direction, then channel A would pulse before channel B, If it turns the other direction, then channel B would give us a pulse before channel A. So what we can do with that encoder is we can tell direction. The speed of how fast the wheel's turning around would tell us the speed of the robot, right? You understand that? But what you're going to have to understand is there's a lot more pulses on there than one pulse per revolution. Because what we want to do is we want the thing to be running at extreme slow speed, and we're not going to sit there and count for 1 minute. We're going to count for probably what? 1 second. Then we'll run through a little bit of math to actually convert it into the actual speed. Well, the problem is the encoder that we got, not that one right there, he gives us 2,100 pulses per revolution. And that motor has the ability to probably run, I don't know how fast. Well, the problem is that the counters that you know of, these are software counters. So that means this counter over here is made up of a bunch of line of machine code. And the problem with programs, it takes time to run. So if we get into what I like about the RS Logic 1100 instruction manual, it tells you the amount of time for every instruction that thing supports. So if you were very interested in how fast something could scan, then you could go into that manual and you could actually look up every instruction and you could add all those times together and you'd know exactly how long it would take your program to scan through your logic. Well, what we want to do is we want to be able, so what we have is on these encoders that are spinning extremely fast, these software counters can't keep up with it. We'll lose counts all over the place. So one advantage that hardware, physical parts have over software is hardware always can be faster. So what happened inside these PLCs, they realized that these counters inside the PLCs could not keep up with these encoders that we're having on these motors now. So what did they do? Well, they went back to hardware. So every one of these counters have a true hardware counter inside there, and they call them high-speed counters. These are not software counters. These are high-speed counters. So you don't program those. You use them, but you don't program them, right? You understand? So you every once in a while you would read the accumulator off that thing or something like that, or you can make it generate an interrupt ever so often to tell you to do what, to go out there and read. So this guy right here's got like 5 high-speed counters inside of it. If we program them and use them. Every PLC that I know of now have high-speed counters in it. And why is that? Because we're trying to keep up with all these encoders and all this stuff that's moving at such breakneck speeds that these software counters just can't do what?
You can only use 5 high-speed counters.
On this guy.
But you can still use the software counters.
Yes. All you do is they're there and they're dedicated to certain inputs. But if you don't configure them, they don't work, right? So you have to go in and actually get into a status file. In fact, it's here. So we'll go up here and where's my program at here? Over here on function files. I don't see it there.
The high-speed counters we just use for large quantities at a fast
Something
rate.
moving at fast speed.
Or a rotator, or like
An encoder, or I've seen where these people that package these cans, they do it so fast now. I don't know if you ever, it just looks like a what? Just a blur, yeah. So, I was trying to figure out where to set up the high-speed counter again. It's here somewhere. It's not there.
So can you also set it up to where?
Oh, there it is, number 1. It's right. It's the first tab. I was looking at the tabs over here. So this is where you go and configure this high-speed counter. And so you would come in and you would have to enable it. So there's probably an enable down here somewhere. And then you can tell it to either what, be an up counter or a down counter, so you can tell it which way to count. And a lot of these things you can do manually inside the function file, or you can actually do it with instructions.
So you could set up the high-speed counter to be like, when it hits 10,000 on the high-speed counter, it hits.
It generated, you can make it generate an interrupt. Or you can set something up where you go out and read it every once in a while. If it's looking at an encoder, what you would do is you would read it and you'd clear it and let it start counting from 0 again. So that makes sense.
Yes, sir. So it can still count
Okay.
like it normally does, but then you could transfer it into a digital counter.
Well, no, you would probably transfer it in with like a move instruction. You wouldn't bring it you wouldn't bring a counter into a counter.
But it's like, like we had the clock set up where for every hour, like if the high-speed counter hit 10,000, it would put a 1 on another counter and then it would reset. You could set it up.
You could, but usually we just let the counter count, and then I don't know what the range on these, we'd have to go out and see, because it's gonna have a physical range just like a standard counter. I don't know how many words, I'd have to go back and research that and see what the resolution or how far these things can count. We would only do that if we exceeded the range of the counter. We'd probably do that. That's a good thing. And then maybe, after 1,000 counts, maybe the software counter could keep up with it, right? So we can set up a high-speed counter to generate an interrupt. I don't know where I'm at. For the 500 series of PLCs, which basically are not made anymore, right? Y'all know that. What you would have to do is you would have to buy a special module that had the ability to generate an interrupt. This guy's got so this guy has a high speed, so this would be for like the 500. This would be for the 1100 either. So what we have is we have several input ports. We'd have to go up and look that you can actually use them. You can use those input ports to generate an No, this is the 500 discrete IOs right here. So a standard input module on the 500 series would not be able to generate an interrupt. What we can do on the 1100 is we can specify one of our inputs to do this input interrupt. We have a selectable time interrupt where we can have the real-time clock generate an interrupt at a certain amount of time. But it's still considered, since the real-time clock is hardware, it's a hardware supported device, then this is still what we call a hardware interrupt. Interrupts a scan of the main PLC ladder program, similar to a subroutine. Most often initiated by what? Hardware. Must reside, so the interrupt service routine must reside in somewhere between the ladder 3 and ladder 255. By the way, on MicroLogic supports interrupts, but on MicroLogic, you don't have the ability to add on the 1000, and this is why we moved, because on the 1000, it's a fixed PLC, which means what? You can't add anything to it. So you can't add additional program files. You can't. So if we looked at the 1000, and I'll boot one up while we're down there, you'll look, it's got one file, it's file number 5, that's dedicated to interrupt service routine. So if you're going to use interrupts on that guy, you got to use what? You got to use ladder 5. So that's something you might want to figure out. 500, you have to buy a special mod. You have to buy modules that supports the interrupts. On the 1000, you have one input that would allow you to use that one input as an interrupt. The 1100 is going to dedicate some of these up here that you can use, but you can use any ladder file. You can use any program file that you want to. That makes sense? So this is why we need to use this instruction. This instruction right here is optional. If you look in the data, your book says it's required. required, but if you read the instruction manual, it says it's optional. But normally we would use it, so that way we would know we'd know which routines are interrupt service routines and which are, subroutines, right? Cause it's very, very similar. It's always scanned as true, it's an input, so we'll have to put it's just like the other one, we would have to put a bit file over on the output instruction. Yeah, you must complete the run with some type of, output instruction. I don't know what unified control device is. So we'll probably, I don't have one of these set up, but I do have one of these set up. So what's the selectable time interrupt? Selectable.
When they interrupt.
So what we do on the selectable time interrupt is that we establish a time, how often this interrupt occurs. So, and it's in milliseconds. So 1,000 milliseconds would mean it would occur every what?
10 seconds? Wait, 1,000?
It would occur every 1 second, right? It would automatically generate an interrupt every 1 second. If I did it that way. Now, when the interrupt occurs, the processor inside the PLC is going to save everything that's going on when the interrupt occurs. It'll go out there and run the specified interrupt service routine. And then when it hits the return, it will do what? It will come back to the next rung in the program.
So like a fault is an interrupt?
A fault would be an interrupt, but it would be an interrupt that we're not controlling. A fault is an interrupt that's built into the firmware of the PLC. These are interrupts that we control.
Sounds like that's question.
We control, these are user interrupts. So you're right, that's a good point. Some of y'all had it fault, right? I think in the math, until we figured out what was going on,
Yeah.
it faulted on that division program because some of them divided by zero. And I did the same thing up here, by the way. But that would be an example of an interrupt. So something happened, but that's built into the firmware of the computer, right? These are yours. You can use these. So you can set up a selectable time interrupt. And these means I can make a program file. I can make one of my program files run at a specific amount of time. So here's where you could go and set all that stuff up at. It's inside function file. And here's STI right here. And you can do it here. So look at some of the things we can do. First of all, we wanted to make it work. We have to do enable interrupt, right? So if I didn't select that, I'm sorry, this is time interrupt. These are all of them. This is what time interrupt. I have to do what I would have to enable it. This would be, what would this be right here? That would be the program file number. That would be a number between 3 and 255. By the way, you don't have to take those program files in order. You don't have to, when you set up a program file, you don't have to go 2, 3, you don't have to go 3, 4, 5, 6. You know, you could go 255 if you wanted to, right? So this would be wherever I put my interrupt service routine at, I would put that program file number right here. Now I have to figure out which one. Interrupt enable. I don't know which one of these are. We'll have to look at it. Now, what would be nice if we could do what, instead of us coming into this file right here, this function file, what would be nice if we could just set it up and go like with instructions within our program. That makes sense. I don't see my documents folder. Let's see if I have this one in there. Is this in the book? So we're inside the chapter on jump subroutines and interrupts. You'll find it. Is it in the book? In interrupts? What does it say about interrupts?
Yeah, it's like I don't think that.
That little section right there.
Yeah, that's it.
So this is RS Logic 500. So here's our instructions we have available to forward it. We have an ISR instruction. What are we going to use that guy for? Oh, I'm sorry, the very first. I'm sorry. INT instruction. What's that? If you use interrupt receipts, this is the book says must, but the textbook says must, I think, but this is actually an optional instruction. But we need to use it, and why is that? Because this guy looks exactly like a subroutine. So we need to identify these program files, whether they're subroutines or interrupt service routines. So ISR says for interrupt service routine. The interrupt service routine must end with a return instruction in the run before the end. The return instruction can be conditional. We have two additional instructions where we can do what? We have an STD instruction, gives us the ability to do what inside our program? Disable the timed interrupt. We have an STE instruction that gives us the ability to do what? Enable. The STI instruction is technically not an instruction. It is hardware generated through the clock circuit in the CPU. So we do not have an STI instruction because this is generated by hardware, right? That makes sense? So what instruction do we have? Let's see if this is. So we have an instruction that they call STS, selectable time start. This is an instruction that we use in our program to tell the PLC to start or enable the selected time limit. Partially configured with the instruction configured through the function file listed in the project group. The STS instruction is located in the file miscellaneous tab. So let's look at this on an actual program. Oops. So the way this guy works, oops. So this makes it a lot easier. This is in milliseconds, so I'm telling it to interrupt how often?
Every 10 seconds?
Every 10 seconds. Now, the way this works, if we put a zero in if we put a zero in here, that disables the interrupt. If we put a time in there, then it's going to generate that interrupt automatically every, what did I say? 10,000, which would be 10 seconds, because that's in milliseconds, right? Okay. So what I have is I have another subroutine over here. This is not a subroutine. This is what we call an ISR, interrupt service routine. And what we have is we identify it as an interrupt service routine by starting off with a what? So subroutines we use the SVR instruction. Identifies that as a regular subroutine. Interrupts we use the INT instruction as the first rung. This identifies it as what we call an interrupt service routine. And this examines true all the time, so we need to put some type of dummy file over here, output over here, right? So what I've got is I got a counter. And then we're going to run this thing. I'm going to upload it. Oh, dang it. That power strip's having problems. So here's my stop. I'm sorry, here's my start. And it went off again. Let me put it in a different plug. Oh, this is stop over here. This is stop. This is start. So notice here we swap the start. Normally we put our stop on the left-hand side. A lot of other people put the stop on the right-hand side. And interrupt these. So I'm gonna come over here on switch 3, and the counter's not run. The counter's not counting. And why is that? Because the subroutine, because the interrupt service routine is not running. So now it should be running. See what it did? Okay, so I'm gonna come up here and enable it. It don't say it's enabled right now. Now it's enabled. Now turn it off. Still says it's enabled.
Count went up by 1.
Yeah, it went up by 1. Right. Now it says it's disabled. It don't say it's counting up yet, right? Now it is. It counted to 6, right? Now it still says it's enabled. It still says it's enabled even though it's not. Now it's counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 10.
Yeah, but the counter went down.
Yeah, but it's not, it's staying enabled once I enable it
Oh, for 10 seconds.
for 10 seconds.
Okay.
So what it's doing is it's not running this, it's running this interrupt subroutine every 10 seconds. right? So see, it's not going true yet. It's not counting because it's not running the subroutine. I mean, not the subroutine, the interrupt service routine. When it comes up and runs it, it counts, right? And then I can turn it off and it's not running this interrupt service routine until every what?
Oh, because the other one set to 10 seconds too. So it has to wait.
Every 10 seconds it runs, every 10 seconds it runs this program right here.
Yeah.
It runs this program file. It runs this program file every 10 seconds. Between those program files, it's running the other program. So I can't tell it. I'm over here, right? I don't know what's going on over there. I can come over here and I can still stop this. I can come over here and I can use this counter down here. I don't know what's going on. This is switch 0. Oh, I'm sorry. That's B3. So this guy here, I don't even see a B3 over here, guys. Undoubtedly I modified this. But what I want to say, this guy here, I'm causing this thing to run that interrupt service routine, but it only runs what? Every 10 seconds.
The other one runs 10 seconds too.
No, this guy runs all the other times. So this guy here scanning a few microseconds, is sitting here going like this, running, 10 microseconds, it runs that one, comes back to this one, runs. Where does the interrupt occur? Where can the interrupt be at? Well, it could be right here when the interrupt occurs. Normally it'll get through with the rung, and then when it hits that return, it comes back to the rung under the ones that call it.
Oh, okay.
So that other routine is running every 10 seconds. How often does this thing run? All the rest of the time. And what we're doing is we're causing an interrupt to occur. So if I needed to check something ever so often, and I needed to make sure it was checked ever so often, then I would put that in an interrupt service routine like this. This is called a selectable time interrupt, which means I can select the amount of time that interrupt occurs. So this is actually running off a real-time clock. It's running, so we don't have an STI instruction, right? You understand that? We have this guy. It configures the STI serviceable time interrupt. And what is the interrupt service routine? The instruction you should start them with. You should start them with this, but it's what? It's optional. But if I've got a bunch of service routine, if I've got a bunch of subroutines and I got a bunch of interrupt service routines, I need to be able to tell what subroutines are what, right? So one thing, giving them a name, make sure you give them a name that identifies what the routine is or the program file is, and also make sure you label. So we use the INT instruction to specify this is an interrupt service routine, whether it's generated. This is are you okay? You keep saying that, Sarah, but I'm not sure if you are. So look, I can come over and flip this. So over there on that other counter, this guy here would be counting. This guy, in fact, if I don't hit it exactly right, it's not going to pick it up anyway. Because when it comes over and runs this routine, it goes through this routine just like that, right? You understand? But now it shouldn't be enabled. So I'm gonna come over and turn on switch 3 again. And how long has it got to wait before it actually counts?
Until it gets part in that.
Until it gets into the interrupt service routine. So we don't call these guys subroutines. We call them interrupt service routines. And an interrupt service routine is it's a program file that's written to take care of that interrupt. Whether it be a selectable time interrupt or if it's generated by one of these inputs. And I don't have a program written for that. So even if I turn that thing off on a regular counter, when I turned it off, it would just say, well, as soon as I do that, right? This has got to wait until what? Every 10 seconds. And then those other thousands of seconds in an hour, it's inside that other routine, right? So it's sitting there looping through that other routine right now. And how long does it take to loop that through that other routine?
It would be like adding something to a line at a certain time. Well, like saying you can only add something to something at certain times because there's flow in between. So like you would set up something like that for it to, like for you to be able to flip a switch and it'll only input it in there when it has the opportunity.
When it has the opportunity, every 10 seconds. But what you're doing is you're guaranteeing that input. You're guaranteeing that input will eventually be honored, no matter how long this program is over. So like I told y'all, if you look at the, I know y'all want to go lab. If you look at the instruction manual, and this is on Blackboard, by the way, the actual true instruction manual. And this is something you need to get used to, because you can get these instruction set manuals for any PLC and you can get them free. Right? You understand that? This book right here is written specifically for what? This book you're in is written specifically for a PLC running RS Logic 500. I'm sorry, that we program using RS Logic 500. So that means if I go to RS Logic 5000, 5000 does the same thing, but the syntax might be a little different. I might not be able to find a textbook written for an RS Logic 5000, but I can go to Rockwell's website and they'll give me the instruction manual free.
But since we have the
It's just like when y'all take operation and programming. There's no book. If we tried to, there's no book that we could use over there because we have so many different what? Robots.
And like it was different between me and Chris. He was on the Panic, I was on the Kuka. And
so what did we make y'all use?
The manual.
The manual that comes with the robot. If you can understand that you can get those manuals for, once you get the robots, those manuals are basically free, right? So being able to look at that. So if you need more information about an instruction, then what you need to do, guys, is you need to go to Blackboard and just go into what? I think it's in the reference material. If Blackboard is, by the way, we are getting a new version of Blackboard.
Wait, there's a new
Starts in
version
the
on
spring.
top of this moving server location?
No, it's a whole new version. And we're not, and the college is not going to host it anymore.
Yeah.
So we're not going to have problems major problems with the college network.
So you are transferring into a data center?
Yeah, they call it a cloud, but it's a data center. Yeah, so
And that claim video. Server goes down, everybody gets mad.
yeah, they had the server go down for some big game a couple of weeks ago. Was that one of them you just played?
Uh-huh. Someone DDoS the server. Just log in. It's funny now because people are going to jail for it now.
I don't game much anymore. It takes up too much of my time. So I have the manual for the 1100 up there. I have the manual for the 500. I have the manual for the 1000. If we could log in. So every one of these instructions take time. And the more time you have, you could literally technically miss inputs. If the programs are long enough, you could literally miss inputs, real rapid inputs, because it didn't do what? It wasn't in that scan. So you come up here and you hit something real fast, and if it's not scanning that rung, you would do what?
Bypass.
Yeah, we would miss it. So every one of these instructions for this one. I'm trying to find just an instruction, guys. What it does when it starts about the instruction, it tells you the amount of time. So the add instruction. Going through, it takes 13.44 microseconds. When the run goes through. It only takes 8.8 or 870 nanoseconds when it goes false. So every add instruction you have, every time the rung goes true, to get out of that rung, it's gonna take what? If you don't have any other instructions in the rung. If you got an input instruction, it's gonna take time to scan that, right? You understand that? So you could literally get into a situation where you miss input. Now, there's two things you can do to avoid that. You can repeat the rung. So the book is a little wrong, but you have to repeat the rung. You can't use an output up here and then use the output down below that in a different rung. You have to repeat the rung. So you can repeat the rung multiple times within, it's got to be identical, right? Within the program, within the scan, which is what we used to do before we had interrupts. But now if I've got a critical input that I need to be scanned, then I could set that thing up for a while, for an interrupt. And when you press that button, by George, it will go to that interrupt service routine for that, and you write it to do what you need to do. And it could happen where? It could happen anywhere within the program. And then when it finishes running the interrupt service routine, it'll come back into your original program to the next rung it was running when it left.
So like when you set those interrupts up, is it gonna prioritize the lowest number?
No, it gives you the priority. So if we was to go in here and look at these interrupts, so the ones that we can assign to inputs, so there's a whole section in here on interrupts somewhere. I'd have to find it, but it does, the selectable time interrupt is actually the fourth down the chain. The first timed interrupt, I can't remember which one it is, but it gives you the priority of the interrupt. And it don't mean it won't be serviced. It means if you have two of them that occur at the same time, then it means, okay, this interrupt right here has priority. Or if it's running a higher priority interrupt service routine and the lower priority interrupts it, it'll wait till it gets through with a higher priority before it allows the other one to interrupt. So the STI that we just looked at, it has the lowest priority of all the interrupts that we use. You know, I know I read it on there somewhere.
I was just making sure there's a hierarchy and set it up that way.
No, you can't. What you would do is you would hook up what you needed to the highest priority interrupt.
Yes, sir.
So this has the, I think EE10 is the second, and the third would be one, and then we have four that we could hook up to an input on our port. I don't see it, guys. Y'all see it? It's in here somewhere. So here's the interrupts. So user fault routine, which would be where you can set up the track faults. That would have the highest priority. And this would be event interrupt 0, event interrupt, followed by the high speed counter, followed by the second set of event interrupts and electrical time interrupts. This would be the priority. So it means if this guy was running and this guy interrupts you, then this guy would scan what it's doing and go and run that, take care of that interrupt and then come back. And that could cause you some timing problems, right? So this guy's got, these are hardware generated interrupts. We use our inputs. We've got 1, 2, 3, 4 inputs we can use. We have a high speed counter that we can set up for it so we can interrupt. It would be the fourth highest, and then this guy we just looked at as the lowest priority. So if you had something that had an extremely high, needed to be ran, no matter what, then you would assign it to this guy right here. To figure out which input is used by that one right there. That would be the one. That makes sense, man?
Yes, sir.
Yeah. So no, we can't set the priority. It's just like those interrupts I looked at over there. Those are not assigned by you. That's assigned by the engineers. That's assigned. Once they say the keyboard interrupt 1, you can't do what?
Change.
You can't change.
So it's hardware.
It's hardwired, but it's set up when they come up
why would they want to interrupt floating around?
Something that messes.
Well, that means if I tap the keyboard on one of the computers running Windows, and it generates interrupt 7, then everybody's going to be screwed up because Windows expects the keyboard to be interrupted via what? Interrupt 1. So that's why once you establish these, you're going to use these were set up by the engineers that designed this 1100 computer. But don't take for granted you get another computer that it uses these things interrupts. You need to get to what? You need to get the manual, and you need to do what? You need to look it up and read which inputs you would use and stuff like that, because y'all can understand why we might have some input that is very, very high priority, like an e-stop button, right? And that would be what? That would be an extremely high priority, right? Where we could cause things to happen when the e-stop occurs, right? Does that make sense? So that's this chapter. I mean, that's just chapter, guys. And like I said, the book has those interrupts out there, but it don't give you enough information, so it makes sense. Hopefully, I helped a little bit of understanding, what's going on, and then are you going to run into these? Maybe not. You might, right? If you want something to occur at exactly the same time, no matter what, then you're going to use these. If you want a high priority interrupt where you go in there and somebody presses an input and that input has to be scanned, right? Then you're going to use an interrupt. You're not going to depend on the what? The scan. You're not going to depend on the scan cycle. You're going to say, well, that input has got to be detected when I press that button. And that's what you do. Are we okay? Okay, let's go lab guys.